use a magnet to change the position of hydrogen in your body, you can then make pretty pictures of the brain with it. And it's with this we can see a picture of this brain here in axial plane, so it's a kind of top-down view of the brain. We can look at sagittal, which is a side view of the brain, and we can look at coronal sections, which are a front view of the brain. So we can use MRI to give us full volumetric views of the brain to understand these end-stage effects of our different lifestyle choices. And in my study, I used a technique called voxel-based morphometry. So when you take a picture, you get an image that is made up of pixels. But when we're looking at the brain, we're looking at it in 3D. So when you have a three-dimensional pixel, we call it a voxel. And so these are box-like elements that make up the image that we can use to measure the volume of any part of the brain we're interested in studying. And in this case, we're looking at the whole brain. So in using this, we can take a normal brain, we can put a whole bunch of brains from different people into the same space. Everybody's brain is different, so in order to compare different brains to each other, we use a series of sophisticated computer algorithms to convert everybody's brain into the same space so that we can compare the frontal lobe in Daniel's brain, for instance, to the frontal lobe in my brain or anybody else's brain that we're interested in studying. And from this, we can generate maps of the brain where we have a view of, in this case, gray matter, that part of the brain that houses all of our neurons. And we can then study the effect of our lifestyle factors on gray matter volume. If gray matter volume is higher, that means our neurons are healthier. But if it's lower, that means that neurons are shrinking and dying off. And this is what we see happen in Alzheimer's disease. So I'll give you an example right here. We're looking at different views of the brain. We're looking at the brain from the front and the back on the top. We're looking at it from the side, and we're looking at it from the bottom. And we see a whole bunch of blobs on the brain, these yellow and red blobs on the brain. And this is from a study I published in the journal Neurology 3 years ago that shows in these yellow and red blobs areas of the brain that are shrinking, getting smaller, where neurons are dying off in Alzheimer's disease. And we see the areas of the brain that are affected include the hippocampus, the temporal lobes, the frontal lobes, and this is very early in the course of the illness. So this is not even when the entire brain has shrunken, and look how much damage we've done already to the brain, and we've seen with Alzheimer's. That's me in front of the Laboratory of Neuroimaging at UCLA, where I did a lot of my collaborative work over the years, and they've been great partners in helping us use even more sophisticated techniques to understand brain structure. So I talked about voxel-based morphometry, which is a way of looking at these box-like pixels in the brain in 3D and measuring gray matter volume. But there's an even more sensitive metric we can use to study the brain, and that's called tensor-based morphometry. So right here we have a smiley face, and we can look at the comparison of that smiley face as a brain, for instance. If this was a brain scan, we can warp it to a template of normal brains and see the change in the smiley face compared to the template brain. And this is another way to measure brain atrophy that's even more sensitive. So the two types of studies I'll be talking about use these techniques. And the Laboratory of Neuroimaging has published 600 papers over the past 10 years in the best scientific journals on these methodologies. So what we're using here is very rigorous, sophisticated science at the cutting edge. So every study I'm going to talk about kind of leads in with a news clip, because I really try to convey my work to the public, because I feel that if the public doesn't understand the importance of how our daily choices affect the brain, they can't take advantage of that. And so the first study I published that got Daniel's attention was that obese people have severe brain degeneration, and this was from Fox News. So you look at this headline, sounds very scary, sounds almost sensational. What I'm going to do now is walk you through the actual science that led to the public's understanding of this information. So I took 94 subjects from the cardiovascular health study, and I looked at BMI. BMI is body mass index. It's essentially your weight in proportion to your height. And the higher your BMI, the more likely you are to be obese. And so if your BMI is above 25, you're in the overweight category. And if it's over 30, you're in the obese category. And normal body mass index, so again, as Daniel said, know your numbers, is between about 18.5 and 24. And I took these individuals and I studied their brains with UCLA's tensor-based techniques to understand if a higher body mass index actually corresponded to a shrinking brain, a brain that was undergoing atrophy with neurons dying off. And the reason there are so many numbers in this table is because I was so concerned about making sure this was as scientifically rigorous as possible that I controlled for all these different factors that we have from our 20-year study. So this is data that very few studies have, and so because of that, I can use them in my analyses to truly isolate the effect of obesity on the brain. So I looked at age, I looked at gender, I looked at education, I looked at race, I looked at whether or not these individuals could have had another process shrinking their brains, like a huge stroke or a bunch of small strokes. I looked at whether or not they had diabetes, whether or not their insulin levels were affected. And I threw all of these variables into our computer models to see which one was the most powerful predictor of brain structure. And so what we're seeing here are the effects of obesity on the brain. We have two rows of images. We have the brain in sagittal, coronal, and axial sections, and we're seeing all of these blue colors. These blue colors correspond to atrophy in the brain when you have obesity. So the more overweight and obese you are, the more these areas of the brain shrink, and we've highlighted them in red below. So what are the areas of the brain that are shrinking? Well, they're your frontal lobes, the front part of the brain. They're your temporal lobes, where the hippocampus sits, which controls all of the big memory and learning functions that is attacked in Alzheimer's disease. And it also affects the white matter, which connects all of these different brain areas together. So obesity gives you a picture that doesn't look all that different from Alzheimer's disease. But these were individuals who didn't have Alzheimer's disease yet, but their brain sustained a huge hit that increases risk for the disorder. And this is something we can control. This is simply another way of me doing the same study where I put even more variables in the model. And I threw in diabetes, I threw in insulin levels into the model, and obesity. Obesity was still the most powerful indicator of brain atrophy. So even if you were obese and didn't yet have diabetes, your brain was still smaller in these areas. Yes?
I know there's been some controversy about the BMI index because it doesn't take age into consideration. So you're comparing an 18-year-old versus a 65-year-old using the same factors of height and weight. Do you have any comment on that? Should BMI be a consistent number regardless of age, or do you think it should take age into consideration?
So that's a good... So the question is, how do you account for age in using BMI as an indicator of the brain? It's a wonderful question, because what we use in our analyses is we actually look at an elderly age group. So we're only comparing elderly brains to each other. There were no young individuals in this study. The youngest person in our study was in their late 60s. So we're drawing conclusions based on the elderly population, although there have been studies showing that people who are in their teenage years who are obese score lower on cognitive tests, and that suggests that there's an effect on the brain of obesity that's negative for children. In our population, we control for age in the study. So what you're seeing here in these red and yellow blobs showing atrophy in the brain from obesity is the effect of obesity on the brain even after you account for the difference between a 69-year-old brain and a 95-year-old brain. We control for gender because, as Daniel has talked about, the female brain and the male brain are different. We control for race. We control for diabetes. And even after we put all of these factors into our model, obesity was still the most powerful predictor. And then we took this study and we repeated it in 700 individuals in 2 different cohorts. One is the CHS, or Cardiovascular Health Study cohort, and the other one is in the Alzheimer's Disease Neuroimaging Initiative, which is a completely different study with different patients, and we found the identical effect of BMI on the brain, and we published that as well.
Was there any difference between the obesity and those patients that had CAD, or are their brain scans the same?
So we looked at the issue. So the question is if people with heart disease have a difference in their brain. The question is a good one, but in our study, our subjects were old enough that a lot of the individuals with really bad coronary artery disease had already died by the time they had been scanned. So you're looking at the effect of obesity on the brain in survivors, in people who are hardy enough to live in their 80s, but it's still a big hit to the brain, unfortunately. So these are individuals who have survived enough to get there, but still you can see the effect obesity has on the brain. This is just another way of showing the same results. I compare people with a BMI above 30, so individuals who are clinically obese, to people with a normal BMI. And we also see similar effects with the arrow pointing to the frontal lobes that controls judgment, attention, executive functions. You see the black arrow in the middle picture showing the atrophy in the hippocampus, which still persists. And you see the green box showing the effect in the white matter and the basal ganglia, which also integrates cognitive functions. Then we looked at people who were overweight. So these are people with a lower BMI of 25 to 29. And you can see their brain atrophy is not that bad. So there's a graded effect over time. Once you pass the obesity marker, your brain really starts to feel the negative effects of obesity. And so we see atrophy with overweight even. So even losing weight from that level down to a normal BMI can also be helpful to the brain. That was a really depressing study, wasn't it? I mean, it was a downer. Daniel and I talked about this. You know, when the study came out, people were so upset and so unhappy, and I felt bad about it too. I thought, I'm only trying to help here. I'm trying to show people a factor they can control. And then I realized you have to show the other side of things. So I've shown something that's really bad for your brain. So the question now is, what can I do about it? What's something I can do for my body that will benefit